Okay, hello everybody. Before we start, preliminary administrative side communication. Does any of you with a Mac have a USB-C to HDMI adapter? Nobody in the class has one? Okay, well, we will start doing it at the blackboard and when we will figure it out in the break. Okay, so, settle in. Welcome everybody to this last episode of Control Systems 1. So you had to have a lot of patience and resilience to get up to this point. We're nearly finished. Vacations are at the doors, or at least breaks from classes are at the doors. We just need to get over these last 2 hours, nominal 2 hours, and we'll be free. So by this time of the class, we have touched upon all the most important topics, of course, of the discipline of control systems. We have seen how control system leverages models, mathematical models of dynamical systems by simplifying them in such a way that we can treat them mathematically in an efficient way. In particular, we discussed in this course linear time invariant systems, and leverages these mathematical models to build dynamic controllers, we call them, compensators, that manipulate the inputs that go in systems in order to obtain some desirable properties in something that we call, thank you very much. No, I'm sorry. Thank you for the effort. To obtain some desirable properties in what we call the closed loop. So if we assume that we have something that we call a system, okay, which we typically represent in these block diagrams with transfer functions, and we call the system we want to control a plant. A system is some relationship between an input and an output. And we discussed how to come up. Can you see down there? Is it big enough? Yeah? So how to come up with something to put in front of the plant that we desire to control on what we call the open loop branch, something that allows us to obtain desirable properties when on the output with respect to something that we call a command or a user-defined reference signal. So a reference signal basically is what you would like the output of your plant to do. So one way to do this is by doing feedback control. Thank you very much. Nope, same as before. It's not going to work. I need USB-C. It's the flat one, like this. This one, yes. Great, thank you very much. But it doesn't have HDMI. We will use an RGB solution. We should have it anyways. This is RGB, here we go. Okay, so, and throughout the class, well, we can get to the slides later. Throughout the class, we saw many ways to first define what desirable means, right? I mean, you want the system to do something, but what should it be? So we identified 3 really important things to do for a controller. The first one is get your system to be stable. What does stable mean? Stable means it won't explode. Or in more technical terms, as time passes, the output of the system or any of its internal states will not diverge, it will not go to infinity. So that's the first most important concern. An output or a state of a system going to infinity, in practical physical terms, means that something will break, okay? Guaranteed. The second important thing that a controller should do is guarantee performances. And performances, what do we mean by performances? So we saw that if we were to think about a second order system, and why second-order systems? Just because we can approximate complex systems with high-dimensional states to second-order systems by considering the dominant poles. If this is time, and this is, for example, if we send a unit input to a signal, then the output could have some, for example, behavior like this. And we defined some performance in the time domain and in the frequency domain. In the time domain, performances basically fall within two categories. The first one is what happens at steady state, what happens after everything in the transient settles down, when time is no longer a factor that influences the dynamics of what is going on. So something that happens down here. In particular, we defined what is the steady state error. And then there's the transient domain performances, which are basically things that tell us how quickly and how accurately, if we want, the system gets to where we want it to be, gets to the reference signal. So we defined, for example, by just defining an arbitrary, let's say, band around what the unit input is, what the objective is, we said, okay, let's take, for example, the first instant at which the output of the system gets close enough to what we need as the rising time. Let's take the time instant at which the output doesn't get away from the reference, the steady state value, more than some epsilon% as the settling time. Let's define what is the maximum overshoot of the system. It is how far away does it need to go? Okay, what is the maximum distance from the reference signal before it settles down? Typically, all these performance metrics are trade-offs one for each other, right? If you want your system to get to where it needs to be more quickly, you might, for example, increase a proportional gain in the controller and make the controller more aggressive, and that would typically imply a higher overshoot. So these are things that one needs to bounce around. And we defined then frequency domain specifications. And the frequency domain specifications are of different nature. We said, well, first, we would like, of course, the steady state error to be something, right? That's important. Because if a system is stable, which is the first of the objectives of a controller, so if we did our job well, the closed loop system at least will be stable. Well, the steady state error tells us what's going to happen when everything settles down. No? So that's a very important first cut specification. But then other important things that we see very well in the frequency domain are, for example, what are the capacity of the system to track fast varying signals or to reject disturbances. So tracking fast varying signals meant, well, if I send a command, a reference signal in the closed loop, what will be the dynamics of the tracking error? Remember that E, the tracking error, which is the input to our controller, is defined as the difference, you can see it here, between y and actually r minus y, right? So if the tracking error is 0, it means our y is equal to r and things are good. We have perfect tracking, right? So we saw that if we wrote the transfer function between these two signals, for example, we can just notice here that y is equal to pu, right? So let's do this thing. Let's just call the open loop branch transfer function, so all this part here, as L of S, okay? So y would be equal to what? It would be equal to L of S times E, right? So from here, we see that E is equal to R minus Y, so this is equal to R minus L E, right? Trivial. So this means that E over R is equal to 1 plus 1 plus L of S, which is 1 plus 1 plus P of S times the C of S. This is what we call the sensitivity function. Super important thing. Okay, when we'll move on in the next course in Control Systems 2 and talk about more complicated systems and multi-input, multi-output stuff, sensitivity function, complementary sensitivity functions are going to be important actors that make us understand how things are going on. So if we want the system to track errors well, so we want this to be a small. If we want, for example, suppose we have a disturbance, so some external signal that is coming from, I don't know, some wind or some factors we cannot control, entering the loop here, we would have the effect of this disturbance on the tracking error. So again, it's how much do these uncontrollable inputs affect the ability of the controller to keep the output of the system at the desired value, are regulated by the same transfer function. So we saw that if we wanted good disturbance rejection and tracking, we needed L of S to be small in some sense. Sorry, to be big or large in some sense that we will define later. And then we saw on the other side, if we had noise coming in, well, this noise is something always unintended, something that typically comes from a measurement device that is being used. It's definitely undesirable. We would like the noise to have very little effect on our output, because the output is what we feed back in the system. So injecting noise in the output means having noise in the closed loop system, which is going to mess up things. We would like to attenuate the effect of noise on the output. And if we go and write the transfer function between noise and output, what we get is the complementary sensitivity function, which is basically this thing here. And it's called complementary sensitivity function because if you sum this and this, which is the same as this, you get 1 for every S. So in order to have this small, we would like to have L of S small. Now, so this, by the way, is the sensitivity function, and we called it S. This is the complementary sensitivity function, and we called it T. So if we would like both the S and the T to be small in order to satisfy these performance metrics that are totally reasonable, it's impossible because T of S plus S of S is equal to 1 at every frequency point. So the question now becomes, hey, but how do we fix this, right? And the big idea that allows us to proceed and come up with all these loop shaping design techniques is recognizing that typically commands and disturbances are something that are strong at low frequencies, where low frequency can be something up to, I don't know, 10 hertz, 20 or 50 hertz, 50 maybe is even high. Well, noises, which come from measurement devices, maybe thermal noise in electronics, things like this, are typically more high frequency. So we said, well, in order to achieve these two objectives, then we can actually do it, as long as we do it in different regions of the frequency domain. So we presented what was let's say I argue, the most important graph of the whole course, which is something that says, okay, let's look at the frequency here, and let's look at the magnitude of what? Of the open loop, of the magnitude of the open loop frequency response represented in dBs, which is something that we called the Bode plot, right? And we said, hey, but if we want a good control system as a system that guarantees good performances, good tracking and disturbance rejection at low frequency, good noise attenuation at high frequency, and a stable system, we want something that is high magnitude of L at low frequency, low magnitude of L at high frequency, and some sort of gentle intersection at the crossover frequency. Crossover frequency defined when the magnitude crosses the 0 dB line. Remember, these are decibels, it's not linear, okay? So typically, we saw that the way this is written is by saying, hey, let's represent this big and small, which is we put in quotes because big and small don't really mean anything if not compared to something, right? So typically what happens is one defines the specifications in the form of, we would like the tracking error to be at most 5%, 1%, n% for signals up to 1 hertz or 10 hertz or whatever it is, right? So this translates into an obstacle, let's say a constraint. We can call it a low frequency obstacle, or W1 we called it. And similarly, the specifications on the noise get translated on the fact that the magnitude of L has to be lower than a high frequency obstacle. And the crossover frequency, which we saw that can be approximated with the bandwidth of the closed loop system, is something that is here. This is the so I think we call it the gain crossover frequency. Okay, so the whole, let's say, one way of seeing control systems, which is the classical way of seeing control system, and it's a very powerful method, is to just pretend that the design of a control system C of S is all about getting the L of S of the closed loop system, that is the series of the C of S and the plant we actually want to control, to have this kind of path, to steer around the objects, okay? The obstacles, the low frequency and the high frequency obstacle. I think this was, we called it like this out of the math we did, right? So okay, well, is this clear? Do you have any doubt on this? It's really important. You're guaranteed to have questions about this stuff on the exam. That's another way of putting it, to stimulate your questions. So this is really important, because once you got this, then everything else is like kind of, well, you don't really need me to tell you what are the control techniques that let you achieve. Once you understand this, and you understand that, well, every time you add a pole to a system, so let's say, at the end of the day, the design of a controller can be seen as coming up with a series of terms, rational transfer functions, that each one allows you to satisfy one of the specifications that the designer, your boss, comes and tells you, right? So typically the boss would come and say, hey, I want this plant to have some specification on the steady state error. I want it to have 0 steady state error for inputs of type of order 3, and I don't know, a constant steady state error for these ramps of type of order 3 that is 2% at most, something like that. So first, typically you get steady state error specs, and these are typically satisfied. How are they satisfied? Let's see if you are keeping up with the content of the course. How do you satisfy specifications on the steady state error? There was only one way of doing it. Yes, sir. Okay, so putting lag elements, what does lag elements do? Lag elements increase the magnitude of L at low frequencies, but introduce a delay, right? So if we said that, so increase magnitude at low frequency means that it drives this up if you design the right lag element. Getting this up means it allows you to satisfy this constraint. This constraint is about disturbance rejection and tracking. So it means how quickly, how well would the output track your signal, but it's more of a transient, let's say, response specification. So the answer is not the lag network. It is close. Sorry, a second. It is close because you are going in the right direction of, let's say, the frequency spectrum. Please? Integrators, exactly. So low, this is the low part of the frequency spectrum, right? If you go very, very low, which is as frequency equals 0, That's what the steady state is. The steady state in time, time infinite, corresponds to zero frequency. And we saw that by seeing that a constant input was an exponential with zero frequency, basically, right? So the first thing you do is typically you add a bunch of poles in zero, okay? I don't know how many, I'll just say H, okay? Where that H really depends on how many are already there and what are the specifications in the steady state. Then we add a gain to satisfy the specifications always on the steady state, for example, but even on the tracking disturbances. And then typically you start designing a bunch of other, let's say, compensators, which you can imagine to be each one like a lead or a lag term. Does this make sense? We saw it last class, right? So why does this make sense? Well, if we saw that the lead and the lag elements, designed appropriately, we will see an example today, allow us to bend the L plot only locally at specific frequencies. Say that for some reason you've got a plant that is like this, okay? So you would like to make sure that this part does not collide with the low frequency obstacle, because that would mean not satisfying some specifications given for hopefully some good reasons by your boss. So what would you like to do? Suppose we are doing an exercise where the high frequency obstacle is actually there. So our current design is barely meeting the noise attenuation specifications. So if we want to fix this, well, you could just multiply everything by a higher gain. A positive gain just translates up in the Bode diagram the magnitude of the open loop response, right? But if we do that, well, the whole red curve would go up. So sure, at some point we would fix this problem, but we would even have another bigger problem here. So if you want to deform this red curve only locally in the frequency domain, you can do so by adding lead and lag elements. How many do you want? Typically, one would consider an elegant design, a design that has the least possible number of those terms. But really, as long as, adding more of those terms only makes it more complicated to implement. But it would work anyways. Okay, so are there any questions about this? Yes, no, maybe? Yes, sir.
We realize that with lead or lag functions and integrate. But does a PID loop exactly do this?
Yeah, so a PID loop can be rewritten as a lead lag compensator. And there was one slide on this last lesson. Maybe it was the slide we got at the last slide of the class, but you can literally rewrite a PID compensator as a lead and lag. And it's kind of an extreme lead lag. You will see that if you check the math and you just factor things in the right way, it would be lead and lag networks that have various extreme choices of the poles of zeros. But thank you for mentioning the PID. I'll do a small parenthesis on the PID. So we said that basically this loop shaping is the most powerful thing that you want to learn. Okay, this will work every time. For whatever system you have, even the ones that are really inherently complicated to control, the loop shaping approach is the one that will make you meet your specifications. But PID is a very commonly used controller, and it's really, really famous. It's like, it's used, it's in practice a lot. If you have to try something quickly, if you want to control a system, the first thing you do is PID. It's like the no-brainer. And this is because it's effective, it's super easy to tune. You just have these three coefficients that you can play around with, and you pretty much know the proportional one will get you stability, the integral one will get you steady state errors satisfied, and the derivative one will make you get better time transient domain performances. And actually, you just need to feed back the y, right? So when you feed back the y, all you need to do, so what is the why? Now, I understand this course is very mathematical, no, and people kind of lose the touch between the math and what is going on in the real world. But why is nothing but an output? What is an output? An output is something you can measure, okay? So whatever it is, depending on your system, say we are, we're big on Duckytown. I don't know if you ever heard of Duckytown. It's like a robotic platform. We have a course here at ETH that you might take later on. And so it's all about self-driving cars, right? So let's say the output of a system of a small self-driving car that is driving around might be, what can we measure? Well, we can do all fancy things. At the end of the day, we can measure, or at least get an estimate of what is the position of the car in the lane and how it's turned around. So those would be the whys. What are the inputs? Well, the inputs is whatever you can send in the system so that it does something and moves. So in the case of a self-driving car, a small robot, it depends on the actuators. It might be some current to the motors. It might be, or if you're thinking about a chemical plant, it might be some position of the valves that regulate flows of different chemicals and things like this. So PID is very effective. Now let's see if we can pick up the example that I brought up. The computer needs to see me in the right direction. Here we go. Okay, so okay, suppose we have a plant like this, now, which is any random plant. It's actually not any random plant. It's a plant that is, what can you notice about this plant? So the plant is that polynomial transfer function up there. What's the first thing you would look at? Just to have a quick and dirty understanding of what you're dealing with. What are the important things we looked at for transfer functions? Like a transfer function, you look at, what yes? Thank you, yes, exactly that. There's poles and zeros in a transfer function, right? There's not much more than that. Poles and zeros and a gain, yeah, sure. Gains don't always get the respect they deserve. But anyways, poles and zeros. So first thing you notice is it has a pole and zero and two stable poles. -1 plus -j, right? The solutions of s squared plus s plus 1. So as long as you have one pole and zero and you have the negative real part of the other poles, then you've got a stable system, open loop stable. So it's great. Then you look at the zeros, which are the solutions, the zeros of the numerator. And they have a negative real part, right? There's two zeros at -10. This means the system is minimum phase. So in the course of this lecture, we will see, well, so non-minimum phase zeros and unstable open loop poles are two big complications in the design of a control system. Are, let's say, the things that make this whole deal challenging and not trivial, especially when you have two control plants that have both non-minimum phase zeros and unstable open loop poles. It becomes tricky, okay? And we will see this directly today. So, okay, we are given a plant like this, and somebody comes to us and says, we want it to be closed loop stable. We want the steady state error to be whatever. In this case, it's 0 for a unit step. We want commands. Remember, commands here, it's a way to, commands is a way to say the reference signal up to some frequency, have to be followed with at most 1% error. The phase margin is bigger than something, 40 degrees in this case, and some specifications on the noise attenuation. Okay, these are all legit specifications that we mentioned. Just to recap, what's the phase margin? Why is it important? Anybody want to guess? Phase margin, you can't run away from the phase margin. So if you don't feel comfortable with it, speak up now because it's the best time. Who wants to give a guess at the definition of the phase margin? Or a definition, I mean, what does it mean? Does it need to be a formal definition? Do I need to pick randomly? Yes, sir.
The angle difference when the transfer function crosses units order.
The angle difference with respect to where?
With respect to 180.
Yeah, sure, 180 degrees, yes. A more physical, let's say intuitive, that's the correct mathematical definition. A more physical, intuitive meaning, like what does it mean to have a very low margin of phase or a very big one?
Well, at least we are far away from making the system blow up.
Okay, yeah, so it's a margin of safety. When the margin of phase is negative, it means the system is unstable, absolutely. And actually, this is something we didn't stress a lot, but if you remember when we defined the time domain specifications, the transient performances, like the rise time, the overshoot, these things like this, are related to the damping of the poles of the second order system. That is related to the margin of phase as well. So the margin of phase gives us information both on the robustness, absolutely, the stability of the system. Robustness in this case means how much can things vary up until the system blows up. So it's robust stability, if we want to be a little bit more precise, and gives us information on the transient. So we typically want the margin of phase to be bigger than something. Typical numbers are 30 degrees, 45 degrees. A margin of phase more than 45 degrees is good. Margin of phase of 90 degrees is amazing, okay? Okay, so this is the open loop transfer function. So it's the equivalent of the red line we have for this current situation. How would we start? So the first thing is what? What was it? First thing was steady state errors, right? So what did we say? We said we want steady state errors to be, first the closed loop is stable, and then the steady state errors to a unit step must be 0. Okay, so is the system stable? We said yes, right? We saw directly from the poles that the system was stable. If we wanted to see it here from the diagram, we would look at the crossover frequency, that point there, when we cross 0 dBs. The margin of the phase, it's bigger than minus 180, means the margin of phase is positive. We're good, system is stable. Okay, so we want to make sure that after we did all our controller, the system is still stable. The requirements ask for the closed loop system to be stable, not the open loop one, right? Steady state error. We want 0 steady state error. No, what was it? Yeah, 0 steady state error to unit inputs. So a unit input is something like this. Okay? It's like a constant. So a constant is an input of what order? So an order of an input is defined as, say you have an input is the command in this case, a reference of the kind t at the, what do we call them, orders, let's call this an O, over O factorial. So whatever, it's just think about the order means the power of the t, okay? So a constant is order 0, yes. So this actually shouldn't be a 0. This is an or bad choicing of, let's call this, what's your favorite letter? Small one. N. You can't use n for this. N is, in control systems, n is the dimension of the state space. M is the number of zeros. S, oh, come on, we can't choose S. We've got plenty of S's around here. So it's a good recap, you see? Then, come on, there's how many letters in the alphabet? I is an imaginary number, no? It's like, come on, let's do an H. What about an H? Does an H work? Okay, so yes, the specification asks us to have a 0 steady state error to an input of order 0. Okay, so if we go back to our steady state error table, which is nothing but, I'll write it here, and no need to change to switch the cameras. So what are we talking about? The steady state error is equal to what? The limit for s that goes to 0 of the sensitivity function, basically, times the input. In this case, it's a 0 order input, so it's e at the 0t. It's a constant, it's 1, right? So by just looking at this and expressing S of S with its definition, it turns out that you need to have, as somebody said before, at least one pole in 0 in the open loop transfer function in L, not on the controller necessarily. So in this specific case, do we need to add an integrator in the controller? No, because there is already an integrator in the plant, okay? So remember, it's not like the controller needs to have n poles and 0, h poles and 0. It needs to be the open loop, okay? Well, we satisfied for free the first couple specifications. Now, what's the next one? Commands up to 0.05 radians per second must be followed with at most 1% error. So first, let's find the 0.05 radians. So this is 1, this is 0.1, this is 0.001. So 0.001, 2, 3, 4, 5. This is 0.05 radian per second. Do you agree? Okay, these are logarithmic scales, so you have to get used to it. Okay, so this is roughly this one here. Now, we want the steady state, what was it? The steady state error to be less than 1%. So how do we figure out? This is the definition of the low frequency obstacle now. Okay, that specification is just telling us where this purple line needs to be. Now let's figure out how to put it there. So we know that I want to make sure we get it right. So commands up to 0. Blah, blah, blah are followed with at most 1% error. This means that the r minus y divided by r, that is the relative error of the output and the command in percentage that is divided by the reference, plus or minus doesn't matter, so the magnitude stands for that, has to be what? At most, so lesser or equal, than 1%. 1% is 1 over 100, right? So this is r minus y, it's e over r, less equal to 1 over 100. This is the sensitivity function. So it's 1 over 1 plus L of S, less equal to 1 over 100. This means that the magnitude 1 plus L of S needs to be bigger or equal than... Okay, now look at this. Okay, little parenthesis here. Forget about this for a second. This is where we need to find the solution, but look at this. So this is the magnitude of S of S times 100 has to be less or equal than 1, right? Correct? Do you all see this? It's just algebraic thing. So this is exactly how we define the low frequency obstacle. This is W1 of j omega. So if you want to know exactly how this thing should be shaped, you have to write it in this way. So what is 100? I mean, what should we add in our diagram? If we want to put, if we want to write down here on this graph, draw the low frequency obstacle so that we're sure we're avoiding it. How do we translate 100 in that graph? So basically 100, how many dBs are they? So remember that something in dBs. Are you sure? Yes, correct. Does everybody agree that it's 40 dBs, or shall we calculate it? Let's do the applausometer, like, hey, or the voiceometer. Do you agree with the 40 dBs? Yeah. Yeah, okay, fantastic. Guys, vacations are coming, come on. Okay, so this is up to the 0.05 radians per second that our boss asked us. This is 40 because it's the 1% that our boss asked us. This is the low frequency obstacle. We've got an error. We've got a problem. Okay, L is crashing in the low frequency obstacle. How do you fix that? Okay, we need to design a controller to fix that. So our C of S, what's the first term we're gonna add? Yes. K. How much? Positive or negative? How much? So what you want to do is to basically bring this up here, right? Because so what we're doing is we're translating this such that we touch the corner. The requirement says the bigger at most equal, right? So if I'm not mistaken, these are 20 dBs. Exactly. You can calculate. I mean, if you have the nice squared paper in front of you, you can tell more easily, but you can calculate it by 20 dBs. So we want a K of 20 dBs, which means a gain of how much? I mean, when we write the controller, we have to write it in linear. Please don't get confused between bouncing between linears and dBs, because it's a very common error, and it's a pity because there's like, yes, 10. Gotcha, okay. That only putting C of S equal 10 satisfies our first, let's say, tracking error specs. Actually, no, this is the disturbance rejection specs. Okay, now what else are we asked? We are asked to phase margin no more than 40 degrees. Okay, now how do we evaluate the phase margin? Well, we multiplied by this K. This K is now necessary. We have to put it there, this 10. Otherwise, we will break the specifications, right? So now this whole line has translated up of pretty much this 20 dBs. Just translated. Nothing else has changed. Do you agree with this? Yes. So how much is the phase margin now? How do we find the phase margin? Yes. Yes. So my drawing is bad, but say we are here. So you go down. This is the crossover frequency. Boom, we're down here, right? So so what's the margin of phase? It's actually positive in this case, okay? Like, the system is unstable. So just by multiplying the whole thing by 10, by putting a positive gain there, we get the system now is unstable because of that ugly dip in frequency that it has, okay? So the specs require a margin of phase of at least 40 degrees. How are we gonna fix this? Yes? A lead element, yes. So a lead element, so we need to design this lead element. That's what I would call an R1 of S that I wrote here, okay? So how would we go about doing it? So a lead element, you remember, it's a pole and a zero. The ratio of a pole and a zero, but we select I always forget it, what is it, the pole or the zero first? Well, if it's a lead element, it means the phase needs to go up first, because lead means it contributes positive phase. If the phase needs to go up first, it means the zero needs to come before the pole, right? Remember, a zero with a positive tau, both the diagrams lessen, phase goes up. Pole with positive tau, it's just flipped over with respect to the x-axis, so the phase go down. So if you mix and match appropriate, let's say you put a zero here and a pole here, and suppose this is the phase diagram, your phase would, if you look at the asymptotic approximation of the Bode diagram, your phase would first go up and then it would go down. So if you sum them up, you get something that goes up to here and then starts going, and then it's constant, right? Because you're subtracting the same amount. No, this is the magnitude, so sorry. For the phase, you would get a behavior like this, and this is the zero, and the pole is here. So yeah, I'm messing this up. Let's do it well, otherwise it's just confusing. So suppose this is the phase diagram. Suppose we have a zero here. Do you remember what's the phase graph of a first order term, or 1 plus tau s? You go 1 decade before, 1 decade after, it goes up to 90 degrees. And suppose this is our zero, so 1 decade before, 1 decade after, this goes down 90 degrees. So a lead element, which is something that goes up and then down, needs to be the pole, the zero before the pole. Okay, so we have R1 of S is going to be something of the kind of, it's going to be sum K times S plus A over S plus B, where A and B needs to be designed somehow. How do we design them? So one way would be having the tables, right? The tables, you can bring the tables at the exam if you want. It's one of those things that should always be in your pocket as a control systems engineer. I guess we can continue after the break. Okay, so welcome back. We're at the last hour of this beautiful course, and please settle. We don't have much time left. Settle means to settle. Okay, so where were we? We were at the point where we agreed that we had to design a lead compensator, yes, to increase the margin of phase. How do we go about and choose the A and B, the pole and the zero in order to do this? Suggestions? Say it again? Yes. So we have determined before, we had agreed that in order to meet the specifications on the margin of phase, which our boss exercise requires us to be more than 40 degrees, and in this case we have roughly minus, I would say, so now we have a margin of phase. This is actually less than 0. We have a negative margin of phase of, what is this? Maybe minus 10 or something like that. Definitely ugly, right? We have to bring it up of, let's say, 40 degrees, 45 degrees. And how do you do that? So you do that, we said, by designing a lead compensator, right? And the lead compensator, we've shown that it's basically the ratio of a pole and a 0, last class. And the question now is, how do we choose the pole and the 0 in order to get that specific lead compensator that actually matches our needs? So, well, the first thing we need to do is understand what we want. In life, if you don't know what you want, it's difficult to choose, to determine if a choice is right or wrong, right? So what do we want? We want to increase the margin of phase of, let's say, roughly 45 degrees, around a specific frequency that in this case is, what is this? Say 0, this is 1, let's say around this point, it's around 2 radians per second, okay? So we've got the crossover frequency is 2 radians per second, and we want to increase our margin of phase of 45 degrees. Okay, now we need to choose a lead compensator to achieve that. It's basically about choosing the A and the B. Suggestions? I would like to make somebody else answer. You're answering all the time. Be brave. You'll thank yourself at the end of the day. Any suggestions? You? No? I done the better under the desk. So, anybody? Please. Please, yes, sorry, nobody else is.
Well, square root of B and B has to be the 2 radians.
Yes. Okay, square root of A and B has to be 2 radians. So A times B has to be 4. Okay, so why this? This because the peak of the phase contribution, which makes sense since we're designing a lead compensator to get the maximum phase contribution that we can, the peak is at the geometric center, which is ratio of A and B, of where we put the pole and the 0, right? So the question is, where do we put the pole and the 0? And that is a function of how much phase increase do we want. And if we just look at the asymptotic approximations, which is what we were looking at before, we see that basically the phase contribution increases of roughly 45 degrees per decade. So we could say, well, let's put the pole 1 decade before the point where we need it, and that would give us more or less 45 degrees. And by the way, last class I said a mistake. The maximum distance to get the maximum contribution was 2 decades, not 1, as was pointed out by one of your colleagues there. Okay, so suppose we want to do A over B, so A times B has to be equal to 4. We want roughly plus 45 degrees, so we choose A to be basically 2 divided by 10, 2 radians per frequency, 1 decade before 2 radians per decade, and then B will come to be whatever it is. So, sorry, this has to be, yes, B, so this could be SK times S plus 1/5 over S plus whatever B comes to be, okay? So, okay, and now we have another, so this allows us to get a frequency bump, basically. Thanks to this extra term, we get a contribution in phase that is probably something like this. So we would bump up the frequency, the phase, and we would meet our requirements. Now, what are the side effects of this? We saw that lead compensators have the side effect of increasing a little bit the magnitude as well. So when increasing the magnitude as well, what we're doing basically is changing a little, this is moving this above a little bit. So we're actually changing the crossover frequency again. So please note, this is an observation that is a general observation. These methods rely on many approximations, the asymptotic approximations of the contributions of magnitudes and phase, to say one. So often in the books, textbooks, you will find these methods under the chapter name iterative loop shaping. So why is it iterative? It's iterative because you do it once, as we're saying now, but then it's not like you go home and you're happy. You test to see if it works, and if it does, then you reiterate. So you go back, you redefine your specification, you do it 3-4 times, eventually you get to something that meets your specifications. So we are trading off accuracy in the procedure with the geometric ease of interpretation. It is good. So we could do all of this by doing the exact math, right? We plug in the numbers and we crank out exactly what are the numbers we need. But it's better to get a feeling of what you need to do quickly by looking at a graph and doing back of the envelope calculations rather than doing the exact math by hand, most probably making mistakes in the process, even because what we'll see in the next courses and in general nowadays, you don't do these things by hand anymore. You use different procedures that often are automated. So really what you have to gain is the ability to make sense of what is going on. An engineer is a person that gives sense to numbers. I tell you 7, and you say, this is right or wrong. It's not about finding 7 quickly, okay? Okay, but then while we add this magnitude contribution, we are increasing the magnitude plot. So what is the next step? The next step is, if I'm not mistaken, the last specification, which is about noise. So it says that noise at frequencies higher than 100 radians per second must be attenuated by at least 40 dBs. So this means that, so 100 radians per second is here, right? So this is here. Attenuation by 40 dBs means you want to reduce by 40 dBs, minus 40 dBs, right? So it means that this is the high frequency obstacle, okay? So if the sketch of the plot is right, we are already satisfied. Does it make sense? I see you have a worried face. Not behind you. Good? Are you sure? It's okay, yeah, you can speak up. No, okay. So if this quick sketch works, then it means that we already satisfied this requirements. Suppose that we didn't. So how would you fix it? Suppose that actually nothing. Suppose that actually we were bumping into the high frequency obstacle. How would you fix that? Yes? You could add a lag compensator. Why would you want to do that? So maybe, let's talk about it. So what does a lag compensator do?
Lag compensator would shift down a little bit the plot, so we would go under the...
Make sense? Yes, yes, that would make sense. Let's say that you would have an intended side effect, though, that might be relevant in this case, because you would be increasing the magnitude at lower frequencies as well. So you would be changing the crossover frequency, and therefore you would probably break your specifications on the margin of phase. So maybe there's another way. That would work, but then you would have to reiterate and probably change the numbers before as well to double check that. So since we're doing things in this order, ideally we would like to always, when we add a new Ri+1, basically, to make so that it doesn't mess up what we did before. So we start from the left of the frequency domain, we move forward, but every time we add a new thing, we would like to add it in such a way that it doesn't perturb what we did before, otherwise we have to reiterate the design. It's not that we can't do that, but it's not ideal. So remember that the magnitude contribution of a pole, 1 plus tau s, steers the magnitude of the frequency response up. Every time we add a 0, this curve gets bent in this direction. Okay? It depends where you put the 0. If I put a 0 here, remember the asymptotic approximation is something like this, so you're adding a positive slope, right? On the other side, suppose I put a pole here, the asymptotic approximation of this term would be this, so it would mean we're steering the red line downwards. So if you want to avoid a high frequency obstacle, what you need to do is bend this downwards of how much you need, okay? So you just add whatever number of poles at the frequencies you need, and that would not, if you write them in a normalized way, with 1 over tau s plus 1, that would not modify the magnitudes before, okay? Okay, so now let's look at something interesting. all of this was for, as we noted before, non-minimum phase system, open loop stable. Doesn't mean we cannot do it for non-minimum phase system and unstable open loop transfer functions, which arguably are the most interesting, because if you have a minimum phase system that's already stable open loop, like we're only talking about increasing the performance, right? What's this chatter? Are there doubts? Yes, no, maybe. No. Are you sure? Okay, so suppose we have minimum phase, a minimum phase plant, open loop plant. Means we have either zeros in the right-hand plane or poles, unstable open loop poles. So poles in the right-hand plane. How do we study? How do we go about it? How do we study? We always say it's a problem, right? Why is it a problem? How do we see it in this context that it is a problem, and what implications does it have in our design of a dynamic compensator? Well, first, we should say that these methods that we looked at are definitely correct, can still be used. But remember, as a general rule, if you're ever in doubt, use Nyquist, because Nyquist is the killer method, is the one that always gives guaranteed results. And in fact, it's the most complicated if you want to kind of understand, because it's a little bit more intricate, or at least traditionally, it's more complicated to understand. So, but this said, the way we go about it to use this loop shaping approach is to basically isolate the ugly part of the plant from the one we know how to treat. Remember that it's always a good procedure to reconduce a problem to a new problem, to an old one that you know how to solve, and then deal with the extra bit, right? So suppose you have a P of S that has some open loop that is ugly, it's not minimum phase or open loop unstable. We just represent it as the product of a minimum phase one, which is what we've been talking about up to now, times another function or a transfer function that we call D of S. How do you obtain the D of S? Well, suppose you have this transfer function here, okay? P of S is equal S minus Z over S minus P. Z and P are two positive numbers, so you've got both an unstable pole and a non-minimum phase 0. Okay? So basically, you pretend that actually those poles and zeros were stable, were good, okay? Just pretend it. So what you do is you take the mirror image with respect to the imaginary axis. So suppose we had a pole here and a 0 here. What we do is we just rewrite it as a pole here and a 0 there. We do the symmetric. So that would mean we just write it at S plus Z over S plus B. But it's not like that we can cheat. It's not like we can add terms, rewrite it as we want. I mean, yeah, sure, we can do it, but then we're controlling a different system, and it's not really the point, right? So we do this, perfectly legit, as long as we compensate. So how do we compensate? Well, we added an S plus B, so we have to remove it as well. We multiplied by S plus Z, so we have to divide by S plus Z. So basically, we did nothing just by writing this. We are multiplying whatever it was before by 1, right? They cancel out. It's just mathematical trickery. Times whatever was there before. S minus Z, S minus P. Okay? By doing this, now you've got a nice minimum phase plant, and whatever else is what we call D of S. What can we observe of D of S? And then we'll even say why we're calling it D among the many letters of the Latin alphabet. So what can we observe about this D of S? It's basically of the kind S minus Z over S plus Z, S minus P, what is it? S plus P over S minus P, right? So it's like ratios of the same poles and same zeros, but just symmetric with respect to the imaginary axis. I know it's not straightforward to see this, but it's kind of, if you want to take some practice. So what's the magnitude? And this is an imaginary number. So every time somebody asks you, hey, what's the property of a complex number? And you have to think about magnitudes and phases, right? So that's really what the question is about. So what can we tell about the magnitude and the phase of this thing by just looking at it? Well, probably nothing, right? I mean, if I look at it, it just looks ugly to me. But especially the phases, it's difficult to tell. But the magnitudes, look, let's pretend that you have your imaginary plane, Well, if you've got a zero, let's say a pole here, a pole in P, and a pole in minus P. Okay, we're evaluating d of j omega for some omega from, let's say, here. Well, what's the magnitude? The magnitude is this and this, right? This is the magnitude of S minus P, and this is the magnitude of S plus P, correct? You can move this point wherever you want, but these magnitudes are always going to be the same, the two contributions. It's like an isosceles triangle, because by definition, we're choosing the poles at plus P and minus P, or the zeros, it's the same thing. So this means that the transfer function d of S will always have unit magnitude. It's a very nice thing. Does this make sense? Yes, right? No? You can say no. It's okay to say no. It's nice that this d of S extra little artifact, mathematical artifact that we put on the side to understand the influence of these ugly terms, minimum phase zeros and unstable open loop poles. It's nice that it has unit magnitude, because by rewriting the transfer function like this, we can analyze the minimum phase part, which by now we know everything about because we've been analyzing extensively. And this extra little bit that does not mess up with the magnitude plot, because the magnitude is unitary. It's 1 at all frequencies. A transfer function that has unit magnitude at all frequencies, by the way, it's called an all-pass filter. But what about the phase? Well, the phase we can't really tell. The phase actually, probably it's going to be a mess. And it's going to probably be a negative mess, something that makes our life more difficult. It's going to be a phase lag. Remember, lags are bad because they reduce the margin of phase, right? So let's look at an example. Suppose we have a plant that is open loop stable, so the poles have negative real parts, but it has an unstable, has a non-minimum phase 0. Well, can you see the colors? Yes, right? So if you look at the minimum phase plant, so we could rewrite this as what? Well, 1 minus S is ugly, right? So let's write this as minus, what is it? Minus S minus 1, right? Is this correct? Yes. S squared plus 2S plus 2, okay? So let's write it as, take just the symmetric of this, so it becomes S plus 1 over S squared plus 2S plus 2, and then we cannot just come up with stuff as we want, so we have to remove it, because like this it cancels out. We have to add whatever was there before, and there was this minus as well. So we consider this to be the d of S, okay? And this to be the minimum phase plant. So if we just plot out the minimum phase plant, we see that it has this magnitude here, given by the top diagram, and the blue line underneath as phase. Well, that's a very nice phase. Why is it very nice? Because it's just between 0 and minus 90 degrees. So it means that at every frequency, wherever we put the crossover frequency, we always have a margin of phase of 90 degrees. In the worst case scenario, 90 degrees, which is amazing, right? So just by looking at the minimum phase plant, one would say, wow, this is an easy system to control. But actually, if one looks at the d of S part, which is called the d because you can imagine it as a bodedemon that sits in your plant. Somebody gave you this little monster, let's say frequency domain monster that doesn't touch your magnitudes, but messes up your phases, typically always making your life complicated. So you can see that the magnitude, in fact, of d of S is always 1. It's 0 dBs across all frequency. It's the red line above there. But the red line below here gives a phase contribution that goes from 360, which is a complicated way of saying 0, from 0 to minus, what is it? Minus pi, okay? A lag of 180 degrees. So now if you look at the combined, in fact, plant, which is this yellow line here, the situation doesn't look as good as it was before. Actually, it looks pretty awful because the more we increase in frequencies, the more the phase lag becomes intensive. And in particular, after this point here, we would go, if we had a crossover frequency anywhere above here, we would have a negative phase margin. That would mean instability. So what is the effect of a non-minimum phase is 0 in a plant? it's that the crossover frequency cannot be too high, because the more you push the crossover frequency at high frequencies, the more you get a negative lag, a negative phase contribution, a lag. So this can be said, in other words, that non-minimum phase zeros limit how much you can crank up the gain of your system, or how much you can push your crossover frequency to high frequencies. This fundamentally means that it limits how quickly your system, your closed loop system, your controller, can react to things going on. It's a big limit on performance. Does this make any sense? It doesn't, I know. I'm just waiting for someone to speak up. So the key thing to notice here is that we had a non-minimum phase zero. We rewrote the math just to have one component that we know how to interpret, and the other one that is the new stuff that comes in because of this non-minimum phase zero. So the part that we know how to deal with is this one. And we see that it's represented by this magnitude line and this blue phase line. Yes?
Why do you get phase margin there that is negative? You always said that it's difference to minus 180.
Yeah, okay, this is just translated up of 2 pi. So imagine it written between, yeah, 360 is a way to say 0. So that the yellow line is actually going from 0 to minus 270. You know what I mean? So it's just to put them on the same graph. So the key thing to see is that this yellow line here, this line here, which is the contribution of the the red line here, which is the contribution of the Bode-Demon, is basically a phase delay, a negative phase that grows the more you increase the frequencies. So if we were to design an aggressive controller, a controller that has crossover frequency at high frequency, say we designed this to be like this, so this is where we have the crossover frequency, well, the margin of phase would be negative, or at least it would be more negative the more we go in high frequencies. And this would cause instability, and instability is bad enough, right? So, non-minimum phase zero, what it does, it puts a theoretical limit to how much you can push the performance of your controller. What if we had instead an open loop unstable pole? Yes?
If you use a controller, like a controller that just cancels this out.
Feed-forward controller.
There's a controller that cancels.
Okay. What you're doing if you are canceling out a non-minimum phase 0, it's multiplying it. If you have S minus 1, which is a non-minimum phase 0, you have to divide it by S minus 1. So you are, I mean, mathematically you can do it as just a number, right? But S minus 1, 1 over S minus 1 means an unstable pole. So you're designing a controller. So a controller is a transfer function, right? So whatever we said about this works about this as well. If you have an unstable controller, it means that the output of your controller, which is the input to the system, is a signal that diverges, tends to infinity. So theoretically, there's no problem. I mean, if you have an ideal situation, the math works out. In fact, it cancels out. Try adding a little perturbation. Try adding plus epsilon. One of the two. You'll get an input error, an input signal, a part that makes physically no sense. Let's just keep that like that, because this always represents a physical thing that has to act on your system. And whatever you can imagine in this universe, there's no such thing as infinity, okay? So you'll never have infinite current, voltage, rotation, whatever it is that you want to do, there's no such thing as infinite. An infinite input breaks your system at the end of the day. So, in fact, one of the nuisances, most common nuisances in control systems is going to be one of the first classes we'll do in control systems too. It's talking what about adding some nonlinearities in the loop that actually makes sense. For example, the input has to be saturated. You must never allow the input to grow too much, because that's either represents a very high cost or it's physically not the case in most situations. So to answer your question shortly, you never, ever, ever cancel out a non-minimum phase 0 with an unstable pole. Okay, just recipe for disaster. Okay, so let's look at what's going on when you have an open loop unstable pole. It's fundamentally the same process as before. You create the Bodedemon by just rewriting the math in the right way. What are the contributions? Where now the contribution here is that we have a so the red line underneath is the contribution of the phase of the Bodedemon, of this. So what's the difference for the fact that we have an open loop unstable pole? And it's a very bad phase lag, minus 180 degrees at low frequencies. But the more we go towards high frequency, the more the situation kind of normalizes, no? Because the phase contribution of the red line is roughly 0 at high frequencies. So what does this mean? Well, it means that in order to get a good margin of phase stability, the crossover frequency needs to be as high in the frequency domain as possible. Because if you had a crossover frequency here, well, then the phase of your system would be, what is it? It would be basically, the yellow line is the combined system. Here it would be actually positive, so the system, okay, minus 100, this would be, you would have like 1, 2, 3 degrees of margin of phase, which is technically okay, but you don't want to design a system with 3 degrees of margin of phase because it means as soon as somebody looks at it in the wrong way, it explodes, okay, basically. So what are we going to do? So what does this tell us? This tells us that when you have an unstable open loop pole, you need to put the crossover frequency at high frequencies. You need to push this omega t as to the right as possible. Let's say, put it up here, okay? Why? Because you get only a marginal, let's say, cost in terms of negative phase added by this ugly Bodedemon. So having open loop unstable poles means you must design a controller that is particularly aggressive. And this makes sense. Suppose you have a physical system that goes unstable. What does it mean? It means that at some point, given an input of a certain frequency, you send in a sine wave of a certain frequency, the output is going to start growing unboundedly. So it's going to grow very fast and go to infinity. Well, if that's the nature of the plant you're dealing with, you don't get to choose your plant. P of S is given to you, okay? It's some phenomenon. Well, then your controller, that is your computer, if you want, in the loop that measures and does the computation and corrects, must be faster than the dynamics of the instability of the natural process. So if you have an infinitely fast computer that can take data, figure out what needs to do, and just push it back, well, it doesn't matter if in the meantime the system is growing to infinity, because our computer is super fast, can fix things in the meantime. There are some designs that are done like this on purpose. There are situations in which it makes sense to design a system that is open loop unstable. Because when you operate near the instability point, things move very quickly. And you can imagine some situations where that might make sense. Take a military jet airplane, you want to have good maneuverability. That means things have to be able to change very quickly, very easily. Those designs are open loop unstable, okay? So what does it mean at the end of the day? It means that unstable open loop poles limit how slowly, it's exactly the opposite effect of a minimum phase 0. Limit how slowly your controller can react. So now try to imagine a plant where you have both. You have an open loop unstable pole and a minimum phase 0. Now you must put your crossover frequency in a very tight frequency domain. And that might be tough. That's where the challenge of designing a control system comes from. The more this open loop pole, unstable open loop pole, and non-minimum phase zeros are close to each other, the smaller the frequency domain range you have to actually draw this thing and make it pass at the right point. Okay? Sometimes it's simply impossible. Sometimes it's very complicated. Very small mistakes can cause very big repercussions on the physical plant. Even because, as we will see moving forward, the next big topic in control systems is robustness, is model uncertainty. So fundamentally, we talked a lot about models, But models are wrong. Every model is a mathematical representation of what is going on. All models are wrong, to quote, this is a quote, I don't remember who, but it's a quote. So all models are wrong, but some are useful, right? So you use the math to help you achieve what you want as an engineer. There's not like we understood what's going on. So depending on the actual plans, typically figuring out the model requires experiments. And experiments, like all things that belong to this, to the world of physics, have uncertainty. So you'll always be given in the real world scenarios plans with uncertainty. So imagine you have this very small bandwidth where you need to make things happen, and you're not even really sure about what the LOS is, because you know, plus, minus, or whatever it is, the accuracy of my instruments. So that's where the challenge comes out, okay? Are there any questions about this? So what about this? What's the summary? Well, the summary is clear at this point. Loop shaping is powerful. You can pretty much steer, it boils down to defining what these obstacles are, and you can steer the open loop transfer function by placing gains, poles, and zeros, combinations of which are called lead or lag elements, at the right spots of the frequency domain. Once you have non-minimum phase zeros or open loop unstable poles, things become challenging. Now, at this point, basically, we could conclude the course, okay? So this is like the last slide of the course. You might say, oh, but you're only at slide 15, there's another 20 slides to go. It doesn't matter, okay? It's not like we need to finish all the slides. This is enough to know everything you need to know. Full stop. But what about so what's going on from now? Well, what are the next steps? First of all, we got to the point where we can come up with a control system, a dynamic compensator, which fundamentally is a transfer function. Complicated as you wish. Now, after you did all your leads, your lags, you just multiply, you get a nasty transfer function. What do you do with that? So, okay, good job, I got this mathematical function, and then how does that relate to the real world? How do I implement it? Then what really goes on in the real world that makes our everything we've set up to now right, but not complete? And most importantly, if you fell in love with this class, what do you need to do afterwards to actually continue study? Where does it make sense to invest your time in seeing things, other things of control systems? So, since we have 10 minutes left, I will not go thoroughly through the next slides. They're pretty self-explanatory, so you can look at them on your own, but I will stress some important points. So, you designed your compensator, you've got something like this, right? A transfer function. So, I will not ask you to ask questions, because time is short, but raise your hand if you disagree with what I say. I want to see a dynamic movement of hands in the class as I increase the speed of my talking and get to the end of this. So we've got a compensator, which is a result of our complicated design, okay? Now, we want to implement it very well. At some point in one of the classes, there was an obscure slide that we kind of skipped through that was this thing called the realization. How do you realize a transfer function? Basically, we introduced it as, so the way we did the course was, you have your state space representation, x dot equals ax plus bu, y equals cx plus du, and we got to transfer functions, right? That was one of the first steps that we did in the process. Then we said, okay, well, how do you flip over this thing? How do you go from transfer functions back to ABCD? Realizations. One of the possible realizations, there are infinite realizations for a transfer function, is this one. It's called the canonical observable, no, this is a canonical controllable form, well, whatever. This is a good realization, okay? What does it mean? It means that if you use this A, B, C, and D and calculate the transfer function with the known equation, you get that thing up there. Quick look, how do you remember this? A is a matrix that has the dimension of the state space, which is the n at the denominator, number of poles. The B is a bunch of zeros and a 1 at the end. C has the coefficients of the zeros. D is whatever the added term is. Remember, these have to be proper transfer functions, right? So keep this in mind. suppose that we have, somebody gives us a state space representation. So you designed your controller, you got to a transfer function, you can literally implement this right away, and you've got A, B, C, and D. Okay? Now you've got x dot equals AX plus BU. So now after doing this, you've got AX dot equals AX plus BU, and Y equals CX plus BU. Is it really like this? Maybe. Kinda. Yeah, kind of. Because really we're talking about the controller, right? Not the plant. So we're talking about how you implement a controller. So that's a transfer function of the controller, not of the plant. So the input to a controller is the error. The output of a controller is what we call the input to the plant. So this is not Y. This is actually U. This U is not U. It's actually E, correct? Because it's the input and output of that transfer function. Nobody's raising hands, so I'm good. Good. Okay, so how do we implement this? Well, typically an implementation of a controller not typically. An implementation of a controller can be done analogically. You can do it by designing the appropriate circuits that implement the behavior that is described by your dynamical equations. Or much more practically, in modern times, you just write a computer program that does it, okay? And how do you implement this thing in a computer program? Well, first of all, the whole point is, given the inputs to the system, the errors, those are inputs, so they're given, what should U be? And the controller design that you did gave you A, B, C, and D, which are now known. So first thing you write is, well, this is an ordinary differential equation, right? You know from other classes that ordinary differential equations need initial conditions, otherwise you can't even start talking about things, right? So first thing you do, you define an initial condition, x equals 0, x is 0, your favorite thing, whatever it is. Typically it's 0. If the system is stable, the initial condition part will die off very soon. So it doesn't really matter. Now, there's a key element to keep in mind, that is, computers don't know how to do derivatives. We'll look at this a little bit more in detail in control systems too, but they don't know how to do derivatives. So what do? We have to approximate derivatives. So we approximate the derivatives with this concept of finite differences. You know, a derivative is an infinitesimal difference. Now you take the limit for the step that goes to 0 of some difference. What if that step is not 0? A computer doesn't understand infinitesimal. A computer, you need to tell them, the step is 10 minus 11, 10 minus 9. It's a number. It's a finite number. There's no such thing as infinitesimal for a computer. So let's call that number delta t, dt. It's the step. So, well, you initialize your initial conditions. You define the step. What do we do in our program? What is the controller? It's a loop. That is something that gets executed forever until you decide that the controller needs to stop working, or when you turn it off or something. First thing you do is you read your reference signal, R, and now the computer knows what R is. Then you read the measurement. The measurement is by definition something you measure and you have, okay? So that's given. Then you have the number, a computer needs to read it. What does it mean? If you have a microcontroller, it means go access the digital input to the digital or analog input and go and pick up the number that is corresponding to that. Then you compute the error as R minus Y. You've got the error, so now we have this part here. And how do we approximate the x dot equals? Well, x dot is nothing but x at t plus delta dt minus x of t divided by dt equals ax plus be, right? So we're just blowing up that derivative that the computer doesn't know how to do with a finite difference. We will see this more in detail later on, but it's what happens all the time when you solve a differential equation with a computer. So this means that x at the next time instant is equal to this x of t plus ax plus bu times dt, where actually u is an e. Okay? So you compute x in this way. You just get the old x that you initialized at the beginning, and you add that ax plus be part times dt. And then you have x. You can compute u directly because c and e are given. C, E, and D are given. They send U to the actuator, so you continue doing this forever, you've implemented your controller. Does it make sense? Now, you would say, okay, but so many of you didn't like the use of Python in this class, right? Now, why don't you use C++? Why don't you use MATLAB? It doesn't matter, okay? Because the logic has no influence on what language you use. And every language has its pros and cons. As you will go forward, you'll thank us for trying to introduce you to Python, I think. So we will not do examples because we don't have the time. I will skip directly to the end of this because that's important. So after all of this, where shall we go? So the only things I skipped are what's the influence of time delays? Well, the short story is time delay include a lag. Lag reduces your margin of phase, sends your system unstable. How do you fix them? There's no golden rule to do so, but lots of approximations. We will talk about these things later on. So how do you go about from here? What did we do? So modern control systems are not something that you go and actually by hand use geometrical, graphical approaches to design your stuff, okay? But all the stuff we studied in this course is really important because whatever you do, whatever black box you use from some supercomputer, fancy paper you read, articulated controller, it's just doing these things, loop shaping, in an automatic way. The more complicated systems you study, multi-input, multi-output systems, argument of control systems too, or nonlinear systems, or things like this that are maybe not even time invariant, whatever. You always reconduce those complicated systems to the simple approximations that we saw here, and you apply the well-understood notions that we saw in Control Systems 1. Control Systems 1 is what gives you the understanding of what really goes on, regardless of how complicated the control problem is. One important thing to say is take as much laboratory practice as you need, as you want, the more as possible, because doing things in practice, the hardware, has lots of nuisances. I mean, everything is exactly as we talked about, but there's extra little bits and pieces that make things more complicated. You need to gain practice with those things. If you give me 2 more minutes, I'll just go through these other points. Control Systems 2 is a class you can take in the next semesters. I will be teaching it. We'll pick up exactly where we stopped from here. And it's basically the natural extension of this. What we will do is talk a little bit about more fancy control systems designs, not based on output feedback, based on state feedback instead. And we'll talk about more complicated systems, multi-input, multi-output systems, and how this robustness issue affects the whole control design. Then there's classes, control goes towards optimal control. At some point you can say, okay, but I don't care about all these details. I want 1%, 2%. I want to think at high level. Give me a cost function. Give me a reward. Give me an objective. And then let the controller do its thing on its own. Let the math figure out the details. So the discipline that designs controllers based on an objective function says, this is what I want to get here in the minimum amount possible of time. By using less possible fuel that imagine sending a spacecraft to the moon. Well, maybe it doesn't matter how long it takes to go there. It matters how much fuel you use, because more fuel means a bigger rocket, right? What if instead we talked about x dot equals ax plus bu? It's very deterministic. Give me a u, give me an a, b, c, d, I'll give you the answer to your problems. Well, what if the best we can do is talk about likelihoods? If I prod the system here, it's likely that this will happen. It's very common in real scenarios. If you'll ever play around with a Duckybot, for example, which are going to be hardware exercises during Control Systems 2, you will see that everything is stochastic. Everything is based on what are the probabilities that things happen. Okay, so this is kind of, see all of this as the average case scenario. Another way of going about is figuring more how to model systems. We've seen that here, like transfer functions, state space representations, all of that starts from a model. No model, no party, okay? Or at least there are ways to design controllers without models, but without leveraging the knowledge of physics, well, how can we do a good job, right? So having a good model is really important, puts you on a path to success. Another important class, very beautiful topic, is recursive estimation. It's basically, sounds very far away because you don't even know what estimation is at this point in time, but said bluntly, recursive estimation is the magic that makes things actually happen in real time and performant systems, okay? If you want a robot to do its thing for real, it's running all this stuff in the background, like it's using plenty of control systems on top of other little blocks that you need to add there in the loop. But the way you actually write the code needs to be smart. You need to write all your algorithms in a smart way such that they run really quickly and they use very little memory. Why? Because so you minimize your time delays and you get good marginal phase and things work, okay? So recursive estimation, it's a big chunk of the modern contribution to this field, and it's beautiful. I strongly recommend you study it. And then finally, model predictive control. Model predictive control is something that this school is particularly strong, has a huge heritage. Some of the biggest players in model predictive control are from ETH. And basically, it's all about how do you leverage the knowledge of your model of the system, the prediction of what's going to happen, to control your system better, basically. So you take your model, you predict the future, you make a strategy, you design a control input based on the prediction of the future, and as time passes, you adjust your prediction every time, okay? It's fascinating and very practically useful control method for very complicated problems. When you have really lots of things and you don't have the mind to have 32 inputs, 44 outputs, optimality, constraints, stuff, model predictive control, okay? Thank you very much. I hope you enjoyed the course and have a good break.